Hello, in this video I'm going to start getting some maths into our radioactivity by looking at decay, half-life and activity. So radioactive decay is a random and spontaneous process. So what do we mean by that? Random means that we don't know which nucleus in our sample is going to be the next one to decay. So we've got some sample filled up with all these radioactive nuclei, and we know that they're all just itching to decay, but we've got no idea which one is next. So we don't know which nucleus is next, which is next, and for a particular nucleus, we don't know when. So we've got two problems for a nucleus. So yeah, we don't know. I've kind of summarized put that in shorthand form, but yeah, we don't know which one of these is going to be the next one to decay, and if we just look at one of them, we don't know what time it will decay. This is completely random, and not only is it random, it is spontaneous. And by spontaneous, we mean that it's unaffected by external factors. So it is unaffected by other nuclei, whether they're decaying or not. There's no kind of weird causality going on here where they're, all sitting around and one of them goes, so the others don't because that one's decayed. But it's also unaffected by things like temperature or pressure or other external factors. So these are all these external factors, and every nucleus is unaffected by that. So yeah, we got these two things then with radioactive decay: random and spontaneous. And that then feeds into the way we describe all of this mathematically, because clearly there's going to be some kind of probability kicking around on here. We know that they're going to decay, but we don't know which one. So each one's going to have a probability attached as to whether it's going to be the next one to decay. And for a particular one, we also don't know when it's going to decay. There's going to be a probability associated with that as well. And as with all these things with probabilities, if you aggregate them up, all of those unknowns become, on a macro scale, things that we can know about and things that we can describe. So we don't know individually at the level of an individual event or an individual nucleus. We don't know what's going on, but aggregate those up and we can say things about events over time and nuclei over time and things like that. So the first thing that we can do, and a lot of this is common sense. If you think of, you've got some radioactive source, how would you go about describing that radioactive source? Well, the first thing you're going to talk about is, well, how many decays are we experiencing, are we seeing, are we recording every second? So decays per second or decays per unit time, whatever way you want to look at it, decays per unit time. Now it happens to be that decays per second are the becquerel, named after Henri Becquerel, who we mentioned in the previous video. This is the activity. So how active is our source? How many decays are we recording every second? So that kind of makes sense. Another thing that we've got is the half-life. So for half-life, this is then the time, the average time for half of the nuclei to decay. So you can see this is then, it's got probabilities all the way through it. We've got average time, you're looking at a big sample and seeing, well, how long does it take on average for half of that sample to have decayed down to something else. So these are two of our big descriptors that we've got here. Another one that we've got is the decay constant, and this crops up in our calculations a lot. So this is denoted with a Greek letter lambda, and what we're looking at here is now the probability of decay per unit time. So this is similar to our activity. So in activity, we had the number of decays per unit time. Here, the decay constant is the probability of a decay per unit time. So we can see a relation immediately here that the decay constant is going to be the activity, so the number of decays every second, divided by the total number of nuclei. So this is then giving us the fraction of nuclei that have decayed per unit time. So that is our fraction of decays, because this is the total nuclei. So that's why it's turning into a probability. We're saying, okay, well, we've had 10 decays in the last second, but what was the size of the source? The size of the source was, well, there was 1,000 nuclei, 10 have decayed in this second. So the probability that one of them has decayed is 10 divided by 1,000, which is 1%. This is what we're doing here. So our decay constant is a probability. We can use all of these, and this is where we get on to, now we know what these things mean, the core of the maths that we're going to be doing in radioactivity, because we can construct a differential equation out of all of this. So we can say, well, we can wonder what's the rate of change across time? What is our rate of change of the number of active nuclei we've got? So I should have mentioned that here just to be clearer. This is the total active nuclei, so it doesn't include the decayed ones. So if this is our rate of change of active nuclei, that is going to be equal to, well, we've got however many nuclei that we've got. These are our total number of active nuclei. The probability that each one of them will decay, if you multiply those together, well, we're going to get a change in the number of active nuclei. And we'll put in a minus sign because this is decreasing. The number of active nuclei is decreasing with time because they're decaying to then be non-active nuclei or active in a different, with a different decay constant because they're a different radioactive source. So we're only looking at one particular source. How is that changing? So we've now got this differential equation here, and we can solve this. We can separate our variables on it. We can integrate n. So we've got 1 over n. That's going to be our integral of minus lambda dt. So if we start at time 0 with an initial sample of n0 active nuclei, and at time t we've reached some number n, then we've got now, so that's our natural log of n between n and n0. That's going to be minus lambda t. So just solving all of that, we're going to get that n equals n0 e to the minus lambda t, just working through your log here, because of course when we bring that out, we're going to get log n minus log n0, which is log n divided by n0. So this is how we're now getting this equation here. Now, A is proportional to n. We can see that here from our definition of the decay constant. So we can also say that A is equal to A0 e to the minus lambda t. So these are our decay equations for radioactivity, and we'll be able to spend a lot of time calculating things off of the back of this, because we can, provided we know what our decay constant is, that we can then say, well, this is the number of active nuclei we will expect after a certain time, or after a certain time we've got this number of active nuclei, so how many did we start with? One thing that's really useful then for solving all of these, because you've got this issue of, okay, we want to know what the decay constant is, or we want to know something about something, because we've got these unknowns, maybe too many unknowns kicking around, is then if we solve this for the half-life. So if we're looking for half-life of T1/2, then n divided by n0, by definition, we're down to a half here. We've now got half of our original active nuclei. that is going to be equal to e to the minus half-life time. So solving all of that, we're going to end up with the half-life is equal to log 2 divided by lambda, which I've just squeezed in. But that's pretty simple mathematics. We can take the reciprocal of both sides in order to get rid of this minus sign here. So you'd have 2 is equal to e to the lambda t. Then we take logs on both sides and divide through by lambda. So we've got this relationship here between the half-life and the decay constant. So, you know, these can be and have been measured empirically. So most materials are now going to have this information that's available. It's all been tabulated out. So you can use this when you're investigating a particular radioactive source in order to make these comparisons so much easier. So an example then of that, now we can see how these calculations are working, is when you get into carbon dating. So I'll just load up a new sheet for this. So just give me a second. Right, so in carbon dating, so what we're saying here is, right, all living things contain carbon. Now this is mostly carbon-12, which is stable, but it has little bits of carbon-14, and that is radioactive. Now this carbon-14 is mostly produced by cosmic rays in the upper atmosphere. So, I mean, cosmic rays are small particles. They mostly come from the sun. It's stuff that gets chucked out by stars. So it's mostly protons. So if you've got cosmic rays, then you're looking at maybe 90% protons, say 9% alpha particles, and then you've got other things. I mean, I suppose you've got electrons, which might be, written that the wrong way, maybe 1% electrons, and then you've got a few other bits. I know that adds up to 100%, but you've still got a few other things kicking around. But mostly we're talking about protons here with cosmic rays. So these cosmic rays they're streaming in on the solar wind. They're coming in from the sun, and they hit the upper atmosphere, or some of them do anyway, and they produce neutrons. So they'll start knocking some neutrons out of atoms. You know, they'll combine with things. These atoms will decay. They'll release some neutrons. So the cosmic rays aren't the neutrons. They're mainly the protons. The protons can then cause the production of neutrons in a whole variety of ways. Those neutrons can then combine with nitrogen, of which of course there's loads of it in the atmosphere, to produce carbon-14. Oh, that should be a 6. I've missed out, getting my numbers and letters mixed up. So carbon-14 plus a proton. That carbon-14 can then decay back to nitrogen by kicking out an electron. So we've got various processes that are going on here where we're going, so the nitrogen switches over to carbon, which then decays back to nitrogen again. But this is one of the mechanisms that we've got. Of course, we've got this prior step of the cosmic ray actually creating the neutron in the upper atmosphere first of all. But this is one way that we can get carbon-14 into the atmosphere. And as I say, it's radioactive, but it still gets absorbed by these living things. It might only be, I mean, it's a very small fraction of the amount of carbon that's actually around, but living things have got a lot of carbon in them. So even if you're looking at tiny, tiny fractions of this carbon-14 around, it's still significant in terms of its radioactive effect. So, you know, we're all radioactive. It's got a half-life of about 5,700 years. So it's decaying pretty slowly. While things are alive, they continue to absorb carbon. You know, they're still living, they're still growing new material. the amount of carbon-14 is going to stay relatively constant. As soon as they die, the thing stops living. This carbon-14 is going to start to decay in the usual radioactive way. So we can then look at a living sample of the same material and say, right, well, this is the ratio of carbon-14 to carbon-12 that we've got in a living sample. Let's compare that to the ratio of carbon-14 to carbon-12 in the dead sample, and hopefully that will tell us how far down the decay this sample is, and that will allow us to age it. Because we've got our A equals A0 e to the minus lambda t. So we can use this, we can compare these and then work out what t is, because we know what lambda is, because we can get lambda from our half-life, because lambda is log 2 over the half-life. So we've got all of the bits that we need here in order to then date it. And we'll go through these calculations in some of the practice questions. But it is literally now just sticking all this stuff in. You've got a measurement here. These are empirical measurements, which are giving you A and A0. We know what that is. Now we can solve for t by dividing, taking logs, and just going through our usual mathematical processes. There are limitations to carbon dating. So it does assume that this ratio of carbon-14 to carbon-12 is remaining constant. If we're dating some dead material from 10,000 years ago or something like that, well, we're assuming when the thing died that this ratio is the same as it is now. Now, is that true or not? Maybe it isn't. Maybe things are, the number of cosmic rays has changed over time. So we're getting a different rate of production of this carbon-14. These cosmic rays depend upon the activity of the sun. So if you had different solar activity, different strength of the solar wind, because that's related to the solar activity, it's the matter that's thrown out by the sun, maybe we'll have a different concentration, in which case you're not comparing like with like. Maybe the massive burning of fossil fuels in the last couple of hundred years has affected the concentration of carbon-14. Maybe nuclear bombs or volcanic activity or whatever. There's all manner of things that could have changed this concentration. So we are assuming that the ratio is the same. That's one assumption that we're making. The other thing is there really is not a lot of carbon-14 around. It may well have this long half-life, but by the time you start getting to around 50,000 years, the levels, we've got these decay graphs that we're always drawing out, where decaying like this, everything's dropping down by half in the same amount of time. So if we drop down to half here after that amount of time, then same amount of time we're halving each time. So we're flattening out this curve, and you end up just getting into noise. Essentially, you can't tell what is the reading of carbon-14 above just general background radiation, and the differences in activity are getting smaller and smaller the further you go in time. So by the time you're getting to about 50,000 years, you're not really getting readings that you can base much on. The error in the reading is too great. It's blended too much into just the background radioactive noise that we get on these measurements. So really we're looking at dating stuff which is less than 50,000 years old, which is still really powerful. I mean, that's going a long way back, but you're not dating dinosaurs using carbon dating. You're dating stuff which is much more recent than that. You're going to need other methods for dating things that are a lot older. I know with rocks and stuff like that, people use rubidium 87. Rubidium 87 has got a half-life running into the billions of years. So that is more suitable then for measuring calculating the life or the age of rocks, because they're long enough ago that we've moved out far enough down the decay curve. This is, part of what's important with it. You don't want to have this mega half-life that means that nothing's decayed because you're too recent. If you try and use rubidium to date some new rocks, well, you're not going to get anywhere, are you? Because there hasn't been enough change in the activity level. You need to have this drop off. So really, you're looking for some kind of dating, looking for a radioactive isotope which is going to be in the most productive part, the most informative part of its decay curve. So not right down the bottom where you can't tell any difference or it's blended into the background, and not right at the top where nothing has happened. You're trying to find stuff which is on the, this intermediate part of the curve. So that's where carbon 14 falls down if you're looking way, way, way into the past, because it's on the flat. So that's what's going on with our calculations. This really comes through with practice when you start playing around with our general decay equation that we've got here, whether you're looking at activity or number of nuclei. So yeah, just skip to the practice questions that I've got on those, and it just becomes even easier when you start doing it, because it's the same stuff over and over again. Pretty straightforward.